Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Grade 11s, so continuing with qualitative aspects of chemical change, we're moving on to molar concentration of solutions. Now in grade 10 we did learn how to calculate the molar concentration, or just simply put, the concentration of simple solutions. But in grade 11 we're going to do a little more complex. Alright, so if you just take a little bit of revision, let's say we had about 10 grams of calcium chloride. Okay, and this was dissolved in water. Okay, and I'm not going to write down the question for word verbatim. I'm just going to highlight some of the key aspects. And diluted to a volume of 250 cubic centimeters. Okay, calculate concentration. Okay, so first things first, in solution of this, this was a grade 10 level question. Okay, the solution here would be to first calculate the molar mass of calcium chloride. Okay, so molar mass of calcium chloride would be equal to, about, calcium is 40 plus chlorine is 35,5, and we have 2 of them, so 2 times 35,5, that should be about 71 plus 40, yeah, 111 grams per mole. That's the molar mass of calcium chloride. And now we can discover the mole, so therefore the mole is equal to the mass divided by the molar mass, which is equal to the mass they said was 10 grams. The molar mass is 111. Therefore, that equals to about 0,09 mole. Okay, which is wonderful. So now we've got the mole, and now we can calculate the concentration. So therefore, the concentration is equal to N divided by V. Okay, so that's equal to the amount of moles, which was 0,09, all divided by, now they said that the volume was 250 cubic centimeters. We need to convert that to decimeters cubed. So to convert centimeters cubed to decimeters cubed, we divide by 1,000. Alright, so 1 milliliter is equal to 1 centimeters cubed, and 1 liter is equal to 1 decimeters cubed. Okay, so 500 milliliters is half a liter. Alright, that makes sense? Am I right? Yes. Yes, 500 moles is half a liter, as 1,000 milliliters is 1 liter. So we divide still by 1,000. So 250 divided by 1,000 is 0,25 decimeters cubed. And if we do that, our answer will be 0,36 mole on top, because that's the mole, and volumes in decimeters, so mole per decimeters cubed. Okay, now that is the concentration of solution in a grade 10 example. But let's say now we come now to a grade 11 example now. Okay, and in grade 11, let's say now we have a question. Okay, we have a question now where we say we have 20 cubic centimeters, okay, of sodium hydroxide, for instance, and solution, okay, and of concentration that is equal to 0,4 mole per decimeters cubed. Okay, and that solution is further diluted by adding 80 milliliters, or 80 centimeters cubed rather, it's the same thing, but 80 centimeters cubed of water to the original solution. And now they want us to calculate concentration of the diluted solution. Okay, so a short way to write that square brackets is concentration in chemistry of the diluted solution. So now what do we do? First of all, when water is added, the number of moles of our sodium hydroxide remains the same. Okay, it's still the same amount of hydroxide, or of our base sodium hydroxide, that will be present even though water is added. Okay, so what do is we calculate, okay, well, the number of moles of NaOH is equal to C times V. That's equal to 0,4 multiplied by 0,02, which is this divided by this in decimeters cubed, and that equals to 0,008 mole. Okay, so this is the amount of moles of NaOH, because when water is added, the number of moles of NaOH in the solution doesn't change. Okay, let's jump to another color quickly. Now the volume of the new solution, however, changes. We first had volume was equal originally to V1 was equal to 0,02 decimeters cubed. But now new volume is going to equal to original volume plus the 80. Alright, so 0,08, and that's going to equal 0,1 decimeters cubed. Okay, so now we have a concentration, or now we need to calculate the concentration now with our new volume. So therefore concentration is equal to the same N divided by V, and we still take the same mole because that doesn't change, divided now by the new volume, and now that equals to now 0,08 mole per decimeters cubed. So grade 11s in the WhatsApp group that I've just distributed, exercise 3.2 is exercise on diluting and mixing of solutions. Okay, so I'm going to take you through question 1, okay, generously, and maybe I'll leave you guys to do some other questions, but I definitely want to take you up at least until 1.4. Okay, so the question that we have there is crystals of sodium sulfate are dissolved in water. Okay, 1.1 says write a balanced equation to show the dissolution of Na2SO4. So the equation goes as follows. Number 1.1. First of all, we write out Na2SO4, okay, sodium sulfate. And it's a solid, remember, because it's in crystals. Right? And we have our arrow, and on the arrow we write H2O, meaning that it's been dissolved in water. Okay, so if it dissolutes, then we're going to have splits up into positive sodium ions, and of course the negative SO4 2 minus ions. Okay, in solution, in other words, it's going to be dissolved in water. Okay, exercises in the WhatsApp group, so just maybe pull that up. Okay, I'm taking you through question 1, so don't panic. So that's now we need to balance it now. So we see we have 2 sodiums on this side, and here we only have 1. So I'm going to just use another color and just pop it in there. Okay, so I've got 2 Na plus SO4 2 minus in aqueous solution. My equation is balanced. That's showing dissolution. Okay. 1.2 asks us now that, or says rather, that 7,1 grams of Na2SO4 are dissolved in water to make up 500 cubic centimeters of solution. Calculate the concentration of the solution. Okay, so here a simple mole calculation first. The amount of moles of Na2SO4 is equal to mass divided by molar mass, which is equal to 7,1. And on our periodic table, we add up the molar masses of each of the substances. and that'll be around 142, just according to my periodic table that I have. Yours might be a little more or maybe a little less, depending. And then, of course, where were we? Let me just see where I am. Yeah, and we put that in on our calculator, so I'm just going to put that in quickly. 7,1 divided by 142 gives us 0,05 mole. Okay, now that we have the amount of moles, we are told the volume there, said that volume was equal to 500 cubic centimeters, which should be equal to about 0,5 decimeters cubed, and we work in decimeters cubed in volume in chemistry. Okay, so therefore we're going to add that into our formula. Concentration is equal to N divided by V. And we're going to add the moles of 0,05 divided by 0,5, and that's going to give us a concentration of Na2SO4 of 0,1 mole per decimeter cubed. All right. Surely that's straightforward. No questions on that, I'm sure. I mean, of course, if there are questions, please go ahead and ask. 1.3. They ask now, what is the concentration of sodium plus ions? All right, these bad boys, okay, in the solution in 1.2. Okay, now we use our mole ratio. Okay, so we come down to 1.3. The mole ratio is 1:2. Okay, so we have a mole ratio here of 1:2. Let me take this away maybe, and let me just add here 1:2. So therefore, all right, the concentration, square brackets again, of Na plus solution, or Na plus ions in solution, is, if that was in 1, because the proportion of 1 is to 1, is to 1 is to 2 is to 1, then that means 0,1 moles of Na2SO4 must have produced double moles of Na plus ions. So it's 0,1 divided by 1 times 2, which gives me 0,2 moles per decimeter cubed. All right, that's for 1.3. We didn't even need to work out anything. And then for 1.4, what is the concentration of SO4 minus in the solution? Well, the same thing, mole ratio, but the mole ratio is 1:1. Therefore, the concentration of SO4 minus, all right, ions is 0,1 mole per decimeters cubed. Why? They are in the same mole ratio. 1:1. We don't need to work out anything. That's what the mole ratio is there for. It's there to help us. All right? If you calculate the moles of one, we can calculate the moles of all by just using the mole ratio. Okay. So I'm going to stop at 1.4 for now. Okay? Because I want to give you 1.5 and 1.6 to do on your own. 1.5 question was, if 500 cubic centimeters of water was added to the solution in 1.2, what is the new concentration of sodium plus ions? All right. And 1.6, if instead of water, 500 cubic centimeters of identical solution of Na2SO4 had been added, what would be the concentration of the sodium plus ions in the new solution? That's 1.5 and 1.6. Okay, can we please do that? I will give you all up until 5:2 to answer that question. 4 minutes. So for 1.5, if 500 cubic centimeters of water is added to the solution in 1.2, which we calculated there, okay, they ask now, what is the concentration of Na plus ions now? And so the volume is therefore doubled. All right. So now we first had 500 cubic centimeters of water. Now we have now we have 1,000 cubic centimeters of water. So in other words, we have 1 decimeters cubed. Okay, and the amount of moles that we had first was 0.05. So by nature, okay, so the concentration that we had there was 0.01. Sorry, the sorry, I'm losing my words here. Let me start again. The amount of volume that we had first was 500 cubic centimeters. We've increased it now to 1,000 cubic centimeters, which is 1 liter. So now we have 1 decimeter cubed. Okay, and now if the volume has therefore increased, that means that the concentration must be halved. Okay, so the volume has doubled and the concentration must be halved. In other words, we had a concentration here of 0.2 and now we have a concentration now of 0.1. Okay, concentration is now halved. It's gone down because our numerator volume has now increased. So think about it like this. Volume has increased. So if volume increases here, your concentration decreases. All right, think of it like that. So now, according to our mole ratio, we had this answer. So now we had to go ahead and times that answer by 2. So if we increase the volume from 0.5 to to 1, all right, we still get an answer of 0.05. And we must times that by 2, we get 0.1. So for 1.5, the concentration is halved because the volume is doubled. So the concentration now of Na plus for 1.5 is only now 0.1 mole per decimeter cubed and no longer 0.2 moles per decimeter cubed. Okay, that's for number 1.5. Sorry for the initial confusion because I was babbling there. All right, and then we have 1.6. 1.6 said now if instead of water we added 500 cubic centimeters of the same solution, all right, what would the concentration of sodium ions be in the new solution? All right. Well, concentration of the solution will therefore not change. Okay, the concentration is not going to change even though we've doubled the volume. Okay, so the volume of, because remember we add in the same solution, so if it's the same solution, the amount of moles of the substance stays the same, and even though volume is increased, the concentration of the sodium plus ions won't change. Okay, therefore 0.2 moles per decimeter cube is still your answer for 1.6. Okay, just have a look at that question again. Balanced equation showing the magnesium nitrate dissolving in water or the dissolution of it. So that is MgNO3. And there's 2 of those bad boys. All right. Dissoluting H2O, or dissoluting, the correct term is dissolving. And that now turns into Mg2 plus ions in aqueous plus the 2NO3 minus in aqueous. Okay, which makes perfect sense. Means how the molecule looks, or the compound looks. So that's the balanced equation. Yes, that is 2 NO3s, 2 NO3, 1 magnesium, all balanced. Okay. That was 2.1. And then to 2.2, calculate the concentration of the solution. Okay, so the number of moles of MgNO3. Okay, well, not put that arrow there, use an equal sign. It's equal to mass divided by molar mass. Okay, now the mass they gave us was 30. The molar mass they gave us, all that we get from the periodic table, if we calculate that, that's going to be roughly about 148,3. Depending on the periodic table that you use, some of them use whole numbers, some of them use ones with decimals, etc., etc. So therefore, that amount of moles is going to be about 0.2 mole. Okay, what do we do is that now we've got the amount of moles, we can find the concentration. So therefore, what we actually need N over V, 0, 2, all divided by the volume. They said 500 cubic centimeters. So that's about 0.5 decimeters cubed. And that gives us an answer there of 0.4 mole per decimeters cubed. All right, that makes sense. Okay. Okay. Now 2.3 said 100 cubic centimeters of this solution is poured into an empty beaker. Calculate the volume of water that must be added to the 100 cubic centimeters of solution to dilute the solution to a concentration of 0.1 mole per decimeters cubed. So it first initially had a concentration of 0.4. We had to narrow it down. Okay, but remember, only there's 100 cubic centimeters of it and no longer 500. So we need to calculate what's the concentration or the amount of moles of that of the substance in 100 cubic centimeters of solution. So we start by saying in 100 cubic centimeters, the amount of moles is equal to the concentration times the volume, which is equal to 0.4 multiplied by 0.1. 100 cubic centimeters is 0.1 decimeters cubed, and we get an answer of 0.04 mole. Okay, 0.04 mole as our as the amount of substance in 100 cubic centimeters. Okay, now we need to find out the volume. Okay, the volume of sorry, what the term I need to say? The volume that needs to be added of water to dilute it to 100 to dilute the concentration to 0.1 mole per decimeters cubed. Okay, so therefore we say C is equal to N divided by V. Okay, and the concentration that we are looking for is 0.1 decimeters mole per decimeter cubed, because it said that in the question. Calculate the amount of water that must be added to the 100 cubic centimeters of solution to dilute the solution to a concentration of 0.1. Okay, so what we're looking for now is trying to find out, if we got that concentration, what would the volume be in the beaker? Okay, so 0.04 divided by V, which is unknown, so we end up with 0.04 divided by 0.1. So the volume that we get there is equal to 0.4 decimeters, which is about 400 cubic centimeters. Okay, so therefore you need to add volume of water. All right, you need to add about 0.4 minus 0.1, because that was the 100 cubic centimeters of solution, and we got a total volume of 0.4. That's going to give you about 0.3 decimeters cubed, i.e. 300 cubic centimeters of water. Okay, to the 100, so you need to add this to the 100 cubic centimeters, so 0.3 decimeters cubed to the 0.1 decimeters cubed to get a total volume of 0.4. This is the volume with for this amount of moles. This is the volume that's going to give you this concentration over here. Therefore, we've worked backwards almost to find the amount of water that we need to add to 100 cubic centimeters of solution to get the concentration down from initially, I think, 0.4 down to 0.1. Are there any questions on 2.3? All right, guys, we're going to go for it. Question 3. Okay, question 3 again, say we have 500 cubic centimeters of KNO3 and it has a concentration of 0.2. Okay, so first thing we want to do is find the number of moles initially. So in the original solution, so we have the C is equal to N over V, rearrange it to C is equal to, N is equal to C times V. So the concentration there was 0.2, and in decimeter cubed, 0.5 was the volume. We basically end up with a mole of the KNO3, the amount of moles of KNO3 is 0.1 mole, the original solution. Now, when you're diluting, the number of moles of the solute stays the same. So therefore, the new solution, okay, therefore, C is equal to N over V, which is therefore also N is equal to C times V, because we need to find out, I need to dilute the solution to get a solution of 0.18, the concentration. So I sub in the concentration as 0.18 times V, because I need to calculate how many cubic centimeters of water do I need to achieve to get that concentration. The number of moles stays the same when I'm diluting, all right? Especially if the original solution doesn't change in terms of the volume, okay? So that stays the same. We haven't poured out any and dilute the poured out version. We're using the same thing, okay? So now we got that. Let's just check. 0.1 is, now we divide both sides by 0.18. And we find out that therefore the volume is equal to, so let's just put our calculator on, that will help, 0.1 divided by 0.18. Alright, we get an answer of 0.5556 decimeters cubed. Alright, and I use this long number so I can round off. If I times that by 1,000, sorry, not by 1,000, that's wrong. What we need to do is to find out this is the total volume that's added. So now we need to find the diluting volume of water. So the volume of water is going to equal this 0.5556 minus 0.5. Now 0.5 was the original solution, okay, to get the amount of volume of water that we need to add. So if we do that, we'll get 0.0556 decimeters cubed, all right, or in cubic centimeters as the question suggested, 0.05556, you times that by 1,000, you'll get an answer of 55.56 or 55.6 centimeters cube of water that needs to be added to the original 0.5 or 500 cubic centimeters to get the solution down from 0.2, which is basically 0.20 to 0.18 mole per decimeter cubed. All right, and that's that question. In grade 11s, that wraps up the end of this session tonight. Thank you so much for joining us. Please stay tuned. Next week we'll have a look at reactions with a limiting reactant.